Hi everyone. Thank you so much for joining us for our guest speaker session today at Ware Lab. We have with us Stella Lee. Stella is a second year PhD student at University of Washington. Stella received her BS and MS degrees from Johns Hopkins University while majoring in computer science, cognitive science, and applied mathematics. Stella will be talking about her latest research paper on Spurious rewards rethinking training signals in RLVR. Thank you so much for taking out your time, and I'll hand it over to you.
Yeah, of course. Thanks for the intro. I'm sure like some of you have heard about Spurious rewards. I'm hoping that this talk would be very interactive. If there's any questions from anyone, feel free to just speak up. I probably won't be monitoring the chat. I'll try to, but yeah, feel free to speak up. I'm here to talk about our recent work, Spurious rewards, rethinking training signals and reinforcement learning with verifiable rewards. Here's my co-authors. Okay, so let me first go through the motivation of how we started this project. So RLVR has been very popular. There have been many progress recently on Koehn models. It's very easy to get gains from RL, especially Koehn models, and we've seen a lot of amazing work trying to explore different rewards or different training methods on Koehn or Koehn math specifically. Including training on one example or unsupervised RL. Then we started asking this question of, does RL actually teach the model anything? Do we still need to scale RL to get significant gains? Given that if we only train on one example, or if we train on like test time examples, both of these cases can give us very significant gains. So we started exploring what is the minimum supervision needed for RLVR. So this was supposed to be one of the papers where we started looking at, what if we did RLVR on like majority voting label? And very surprisingly, we found that training on majority voting label helps a lot. And then we tried like increasingly weak or even spurious rewards. This includes this list right here. So obviously ground truth is what people have been working on. We explored doing majority voting. So this is not only the most common response from, let's say, like 64 rollouts. We also tried to fine tune the model on the second most common rollout, third most common rollout, and even the least common like rollout from like, I guess, just like the initial base model. And we realized that all of these work. And then we started thinking about like, what happens if we use just like increasingly weak labels? So we reproduced one-shot RL, very, very cool work to use only one example. And then we tried to just do RLVR on format reward. What this means is that like if the response contains /boxed, then we reward the response regardless of the accuracy. And then we also tried incorrect label because we're thinking, like if we're training on the majority voted labels, even like the least common, there are still some responses that are majority voted, or like I guess there's a lot of responses that are obtained from majority voting that is actually correct. The model could just be learning from the correct subsets of the majority voting labels. Therefore, we removed all the correct subsets, and then we used all the incorrect labels to do RLVR. And then we realized that this still gives us pretty significant gains. Lastly, we're like, what if we just randomly assign rewards to responses regardless of any like content from the response? So we tried like different thresholds for random rewards as well. Our main experiments are on like randomly 50-50 chance to reward a response, but we also tried like increasingly sparse rewards. For example, we just randomly reward the response 0.001%, 0.1% of the time. And we realized that although the conversion speed is slower, it still works. So that kind of just led us to like ask the question of like, what is exactly happening? So here's kind of just a performance on Koehn base that like all of these rewards brings us some significant gains. And then this is even more impressive on Koehn math. Even random rewards gives us 21.4% gains on math 500. And we also have M.S.E and M.E 2024 and 2025 results in the preprint. Amazingly, it's really cool that M.E 2025 is after the training cutoff of all of these models, but the Spurious rewards can still bring some amount of performance improvements. So yeah, like these are more like detailed training dynamics on Koehn 2.5 math across different model sizes. So we tried 1.5B and 7B and on different data sets. So all of the proposed rewards improve performance within the first 50 steps. Ground truth are obviously the best signal, but alternative rewards are not that far behind. Except for random, you can see like the purple line, it improves slowly in the beginning, but then for most of the runs, random eventually match up the performance of most of the other rewards. And even here for Koehn 2.5 math 1.5b, you can see that like there's a slight improvement on random, but we only reported up to 300 steps. We left this one running for 1K steps, and it actually like matched up the performance like towards the end of training. So yeah, these are just very cool and like amazing results. So we just thought about, oh, like we should try it on other models. Maybe we just figured out that like training on random rewards would work as a training signal. So yeah, we thought we solved RL, but actually no. So when we extended these rewards to other models, we see quite different trends. So these are the results on Llama 8B instruct and OMO 7B base. So we hypothesized that this is just an artifact of some certain model families. So we later also tried instruct models and basically a whole range of models: Llama base, Llama instruct, OMO base, OMO SFT, Tulu 3, which is an instruct model, and then also Koehn math instruct and Koehn base instruct. So yeah, like we see pretty different patterns when training on Spurious rewards for all of these other models. Just a spoiler, instruct models also, like Koehn math instruct models also does not show significant gains. We suspect that this is because they're already RL trained, so the gain is already saturated. But yeah, then we set up to explore why the trends on like all of the other models are different. So yeah, again, here's more detail on other models, on like the training dynamics. As we can see, the green line is ground truth. So just as a sanity check, ground truth does bring us some improvements for most of these models. And even for like Llama instruct models, the 3B model, even like majority voting and incorrect, for instance, some like minor gains, including one-shot RL on Llama instruct, it slightly improves the model, but not as much as the Koehn math models. So what does this mean? What does this mean in practice? So we recommend that seeing all of these different like trends and like also different scales of improvements, researchers should verify proposed algorithms on multiple model families, of course. I think this was like a pretty standard requirement before RLVR times, but mostly recently, a lot of exciting RL algorithms are only experimented on Koehn math models. Other than this, we also think that the results should be verified against Spurious baselines. Let's say if we just did RLVR on format reward versus if we did RLVR on ground truth rewards. The difference between ground truth RLVR and format reward RLVR would imply some sort of like actual math reasoning ability that the model is learning, rather than just like the model learning how to like make its response more parsable. Another thing that we want to like kind of emphasize is that training, like transparency of the training data is extremely important for research. So in our paper, we did try to look at like what might have happened in all of the different models training stages. But because we only have access to the entire training data and training pipeline for OMO models, we can't actually make any conclusions. So all of these exciting different trends and patterns would be more easily traced back to training to lead to more scientific insights if you know there could be more transparency in like training data and like what's happening in pre-training and mid-training. Yeah, so here are just, I guess, more interesting results on how like the algorithms that works on one model doesn't necessarily generalize. So there have been a lot of very interesting Koehn-centric methods that show weak supervision works mainly for Koehn math using, but then we showed that like when we tried to do the same thing on other models, although just a disclaimer, we didn't try to like do extensive hyperparameter sweeps. So it's perfectly possible that like with other hyperparameters, these algorithms can still bring gains on other models. But we show that with the default pretty reasonable hyperparameters, there's not as significant as the gain on other models. And then if you can see on the right, we have one-shot RL. The gains is very significant for Koehn math and Koehn base, but like not really on other models. And TTRL, even Koehn base, we don't see as significant of a gain. So then we kind of try to explore like, okay, so now we figure out that Spurious rewards work on Koehn models, but not on other models. But we want to understand why this is working. So our initial hypothesis is that RLVR at the current academic scale works by eliciting existing behaviors that have already been learned during pre-training. So the main difference between all of these model families is that, especially Koehn math, it's optimized for math problems during the pre-training and mid-training stages. Therefore, like we assume that there is a different model prior compared to other more general purpose models such as Llama and OMO. So yeah, like we observe one interesting behavior when we try to qualitatively look into the data, and we call this code reasoning. So what code reasoning actually means is that when the model is prompted to answer a math question, instead of, okay, like how a human answers a question is like they'll try to like write math equations and like reasoning through like step-by-step proofs and stuff like that. But what we observe with large frequency is that Koehn math models tend to generate Python code and then to solve the problem. And then more interestingly, they have this output of the code execution after the code generation as well. But during this full like response process, the model does not have access to a code interpreter. So this output is just generated autoregressively from the model. And we can see that like this output is extremely precise. I tried to do the same on my phone's calculator, and I get one fewer decimal points. So we found that this is extremely interesting. And what's more interesting is that this is not pure memorization. We tried to do numerical perturbations of randomly sampled math problems as well. So like this particular example is not in the training or the test set. But when we try to prompt the model with this question, the model can generate the correct code with the numerical perturbed questions and give us the correct answer. So we thought this was super interesting. Koehn math basically learned its own like code interpreter ability based on like what it's doing. Yeah, like even before any RLVR. And then we try to see like, oh, what if we go one step further? What happens when we semantically perturb the question. So we try to like manually rewrite the question. So basically we're asking about the same thing, but just like kind of like giving it a story, like a word math problem, basically. So the model has to do the exact calculation, but the problem is a bit different. And then we realized that the model did not generate code anymore, and then it tries to do like step-by-step math reasoning. So here is some spoilers on our follow-up project, actually. So this is not part of the Spurious rewards paper. We tried to do membership inference attacks on Koehn math. And we see that, so this is a lot of different models, as we can see on this legend, Koehn math, Koehn, Phi, Llama, and other models. So the metric that we're seeing here, this is a very fresh of the like experiment plot. So excuse the visual, but basically we calculate the average loss difference between questions and its numerical perturbations, and we find that the similarity in Koehn math models is higher than Koehn math and Koehn models is higher than other models. So we found this super interesting. And here are some other, I guess, just membership inference attack results. Again, excuse the visual because it's very new. But we can see that like on the left, Koehn math 7b, there's a high concentration of GSM-AK. And then on the right, what we can see is this numerical perturbation similarity compared to the original question. The similarity is extremely high on like math problems compared to code and natural language. Yeah, so that was just a detour on like what happens with code reasoning in terms of like actually in Koehn's model and like data. But again, back to the exploration in our original paper, we found that Koehn math is extremely good at using code out of the box, and RL increases code frequency as like one of the most prominent observations that we saw. So the table that we have on the top is the model's behavior before doing any like RLVR. So this is just like after SFT. If we look at Koehn math, it has a very high code frequency. So it tends to use code reasoning to solve the math problems 65% of the time, and has a very high accuracy when it uses code compared to the 35% when it does not use code. And then Koehn math 1.5b has slightly lower and worse accuracy, lower frequency and worse accuracy, but it is still like over 50% of the time it uses code, and the code accuracy is higher than the language accuracy. But we see some different patterns when we look at Koehn base and OMO SFT. So the code frequency in Koehn base and OMO SFT is actually extremely high. So like we're not saying that the code for reasoning is unique to Koehn math models. In fact, OMO SFT has a very high code frequency as well. But what's interesting here is that for the Koehn base model and OMO models, the code reasoning accuracy is much lower than if the model just used natural language to reason. So here we call these two models bad code models in our paper. So that means like it likes to use code, but it's not that good as using code reasoning yet, I guess, at least before RLVR. And then for all the other models that we looked at, for example, Llama base, Llama SFT, and then OMO base, there's like the model just like doesn't tend to use code at all. There's like 0.2% of the time that I use code. As I was saying, since the OMO pre-training and mid-training data and recipe is completely public, since OMO base does not tend to use code, but OMO SFT uses code, we suspect that maybe this could be from mid-training. And then let's look at the plot on the bottom. So there's a very clear correlation, at least in the first few steps, that like the overall accuracy increases pretty sharply, and the code frequency also increases pretty sharply. But I think a very interesting thing is happening at the later stages of RLVR training. We can see that code frequency drops for the ground truth label and majority voting label. So these two are the kind of highest quality rewards that we're using. So this implies that Although code frequency quickly reaches a peak, this is the easiest way that the model can learn to boost its accuracy. But as we learn more from ground truth labels, the model actually learned to use natural language to reason more and more throughout training. And as we can see to the left, the accuracy of ground truth is still very high. It does not decrease when code frequency decreases. But if we look at the random reward, which is purple, the code frequency keeps going up. And then this is how the overall accuracy is also like correlated with this increase of code frequency. So we thought this was super interesting. And then we tried to look at these similar like relationships between overall accuracy and code frequency in the other bad code models. So if we look at Koehn-Base, this is very interesting. So as overall accuracy goes up for ground truth reward, majority voting reward, and incorrect reward, code frequency drops very significantly. So if we remember, for Koehn-Base, the code accuracy is significantly lower than the language accuracy. So we hypothesized that the model is just learning that, okay, like if I use language, there's a better chance that I get this problem right. So it learns to use language a lot more with the meaningful rewards. Whereas for format reward and random reward, the model does not get that good of a sense of correctness. So then like it stays quite constant as well as the accuracy. And then for OMO SFT, we see a similar trend where if the model is bad at code reasoning, training on meaningful rewards such as ground truth will decrease your code reasoning frequency to increase the accuracy. But for OMO, we see that like other rewards have less of an effect on the model, on changing the model in general. So there's not too much of a difference for like majority of voting or random. Okay, so here is a more in-depth analysis on like what is going on for the model's switching behavior from code to language. So I guess this plot might not be the most intuitive to read, so I'll explain it step by step. For ground truth, we start off with, for all of them, we start off with having 325 problems with code reasoning and 175 with language reasoning. Out of the all the problems that the model started off using code, if we do RLVR on ground truth rewards, actually 160, so like half of these problems switch to using language at the end of training. Therefore, the model might be learning some like actual like reasoning abilities with language. And then there's also a significant number of problems where the model stays code reasoning. And then for language reasoning, the problems that started off with language reasoning as well, some of them, like a small number of them went to code reasoning, and then a lot of them stayed as language reasoning. But we see very different patterns for other more spurious rewards. For example, let's focus on format. Out of all the 325 problems that started off as code reasoning, almost all of them stayed as code reasoning at the end. When we looked further at the data, we had a qualitative conclusion that if the model used Python code to reason, it's more common for the model to use the / box in its final response. So yeah, code reasoning is very closely followed by like, I guess, the parsable response, and which is why after format reward, the model tends to stay in code reasoning. And then there's like a large portion of the originally language reasoning problems that are also converted to code reasoning. Same with like the incorrect rewards and random rewards. So for each of these conversions, so like code to language, language to code, and language to language, we wanted to see like which conversion or like switch pattern contribute the most to the improve in terms of performance. So we average all of the different rewards in terms of the improvement in each category. And then we find that when the model switches from language reasoning to code reasoning, we have a significant gain in terms of accuracy. That means that initially the model is not that good at language reasoning. Therefore, what RL is teaching it is that, oh, like if you got this problem, like if you use language for this problem, maybe if you just switch to code, oh, you like get it correct. And this is what like happened in Koehn math models, that like when it switches to code, the accuracy went up significantly. There is one exception though. If we look at the ground truth flowchart, the accuracy gain from language to language. So that means when the model chooses to use language before and after RL, there's a very significant 60% improvement. So this means that like ground truth is actually teaching the model something other than just using codes to answer the questions. Although I want to note that, so for the portion of the calculation that is language to language, for all the other rewards, there's barely any samples. So like we'll have like 23 samples for format. So like the noise on this last row would be very high. So read that with caution. And then yeah, we see the same pattern for Koehn Math 1.5b. But then interestingly, remember for the bad code models, for example, Koehn Base, we see a significant gain from code reasoning to language. So when the model is extremely bad at code reasoning, but better at language reasoning, what RL is doing is it's actually teaching the model to just switch to language reasoning, and then you can get a really good performance gain. So yeah, we thought that this process was extremely interesting. So if our hypothesis is true, RLVR with Spurious rewards basically elicits existing behavior that correlate with good performance. Then we should be able to achieve so by eliciting the same behavior using other approaches. So instead of just doing RL on the model, if we assume that code reasoning is the most important key behavior that like allows for a higher performance in Koehn math models, then like if we just like force the model to use Python, we assume that this would also lead to performance improvements. So we did something extremely silly. We just prompt the model to start with, let's solve this using Python. And then we also tried another one where as long as the string Python is in the model response, we reward the model. And then if it's not, we don't reward the model. Extremely surprisingly, if we just prompt the model to use Python, we see a 24% improvement in Koehn Math 1.5b and a 15% improvement in Koehn Math 7b. Whereas for the other, and then also for Koehn Base. But for all the other like bad code models, we don't see an improvement. We see like a pretty significant performance drop in the other models when we prompt using, like just tell the model to use Python. And then if we do the RLVR, where we just reward the model, if they generate the string Python, we also see a pretty sharp, significant, performance gain on the Koehn math models, but only in the initial stage of training. And then we see kind of a collapse where for some of the samples, the model just says Python, Python, Python. So this is not that surprising. It happens a lot when the reward is extremely hackable. Yeah. So one more verification, because we thought that this reward design is extremely interesting. If we find that something is helpful, we just go all in and then kind of just make the model do Python. To kind of explore the effect of like, to avoid any collapse, we want to see like if we just force the model to learn without code reasoning, how much gain can we get? So like if we force the model to only use natural language reasoning, we wonder whether the Koehn math, especially the Koehn math models, loses the ability to kind of learn from this kind of rewards at all. So we design a compound reward where we use some other Spurious reward or correct rewards plus no Python. So for example, if this format without Python means if the model generates a response that contains /box and that this response didn't use Python, we give it a reward. But if either of these is not met, the response is not rewarded. So very interestingly, the compound reward where we discourage Python is solid line, and then the original one is where we don't care about whether Python is used is the dashed line. So we can see that like for Koehn math models, just on format reward, if we disallow Python, it's extremely hard for the model to learn any new information. So this is a solid purple line. And then, but for Koehn-based models, as we saw, like not using Python is actually what's helping it to reason better. The solid green line improves a lot more significantly than the original reward. So like this is a lot of lines on this plot. So if you're interested, you can look more into it in the preprint. But basically, we see like slightly different learning trends for also the incorrect and ground truth rewards. So like, especially, okay, let's talk about the ground truth a little bit too. If we ask the model to not use code, but we teach the model ground truth, we can see that like Koehn math models learns, but much slower. So then like the model does not have the shortcut to just use code anymore. We're not saying that the model like is not learning anything from RLVR, but if we like disable this shortcut, the model still learns, but like much slower, and it converges to like a lower accuracy than if we allow the use of code reasoning. So yeah, code reasoning is just like one of the example behaviors that the Koehn math models are using. So we looked into some other like qualitative examples from the outputs and realized that repetition is another thing that kind of just like boosts the model's performance. So the model would just like repeat what it's saying like multiple times. So basically, so when there's too much repetition, it hurts the model performance. So we designed a reward to stop the model from repeating. So you could look into the paper for more detailed metrics, but we designed this metric to count the amount of degree of repetition in the model response. And then if this basically repetition metric is over a threshold, then we do not reward the model. So the no repetition reward also helped Koehn math to achieve a great significant performance gains within like the first 20 steps. So yeah, like repetition is another kind of behavior that is similar to code reasoning. So yeah, like we talked a lot about like all the random things that we did. Now we're kind of like taking a step back and like thinking about more systematic analysis on like why everything is working. So first, for training from incorrect rewards, this partially functions as a format reward because regardless of correctness, even if it's incorrect, it should be parsable. And also, when the response itself is incorrect, the reasoning can also provide some useful information to the model. So yeah, like a few of the another hypothesis is that some of the incorrect responses that we're using as label, they're similar or just variants of the correct answers, but it's just like not parsed by the parser. So there's actually a lot of problems in like current evaluation, as we all know. But yeah, like this is some of the reasons why incorrect rewards might be working. There's also recent works on entropy minimization that says that implies that if we train on like meaningful reasoning traces, we can also make the model learn some meaningful behavior. So now we think the most curious case is the random rewards. Like, why does it work? Like, if we're just randomly rewarding the model, regardless of the response at all, we also see the like 20-ish% performance gains. So we first ablate on different random thresholds. So this flat line is if we just never reward the model on anything. So like intuitively, this should stay flat. But for all the other random thresholds, as long as we reward some of the response, like completely randomly, although there's a lot of noise, the model eventually converges to like a pretty high performance level. We thought this was very interesting, but initially we had this hypothesis of why this is working. So there are more code reasoning than language reasoning in Koehn math, right? So a randomly assigned reward at uniform random, it would assign more rewards to code reasoning than language reasoning. So this is an intuitive explanation But then we looked closer into the GRPO loss and then realized that this is actually not what's happening. So I guess like we just wanted to clarify that like this is a very good intuition, but we did figure out that like this is not like actually what's happening, because the advantage calculation in GRPO, we have the advantage term that is basically normalized by the average reward. What happens is that this normalization term, a reward of 0 penalizes the response code reasoning equally. And then, so basically, if the code reasoning response is likely to be rewarded, it is also more likely to be penalized compared to language reasoning. So the expected advantage of code reasoning is actually 0 for uniformly random rewards. So this makes us question like what is actually happening. And then we did have this sanity check period where we're like, okay, like maybe there's a bug. But then we looked more closely into what's happening in the GRPO objective. Okay, just a spoiler, there's no bug. We actually figure out what's happening. So just yeah, like we're not using the KL term, following a lot of prior work. And then we find that this clipping term in the GRPO loss is actually what's making random reward work for RLVR, for Koehn math specifically. So let me go a little bit more in detail on like how this clipping term works. So as I was saying, the expected advantage is 0, but there's this thing, gradient bias. So there's a difference between the expected gradient with and without clipping. So when the advantage term is 0, this bias turns out to be non-zero for random rewards. And this induces a direction of updates that eventually lead to the model prefer code reasoning more. So what is happening is we take the expectation of the loss, and then we realize that the clipping, this gradient bias, or we call it clipping bias, is actually discouraging the model from leaving the clipping region. So this is a visual explanation. So there's the like old, like the old model and the new policy model. So the GRPO loss is computed on like the ratio of the current model and the old model. The old model is the model that generates the rollouts, and then the new model is the policy model after a few gradient updates, depending on your batch size. So if this ratio, if the new model deviates from the old model too much, outside of this clipping bounds, it gets clipped, and then there's no gradient update depending on the direction of your advantage. So what happens is that for any generation, for any tokens that with the high initial probability, this makes the clipping region wider, because the clipping region is actually decided by the probability of the old model times this 1 plus epsilon term and 1 minus epsilon term. So basically, if the original token probability of this particular rollout is high, then it's less likely to get clipped. So it's more likely for there to be a gradient update for high likely tokens. So what this means is that like if some tokens are initially just like very likely, then it's more likely to be like amplified by this GRPO loss with random rewards. So as we saw before in one of the tables, 65% of the time Koehn math uses code reasoning, but then 35% of the time it uses like natural language reasoning. So let's just think from a high level. If you're interested in the actual math, you can read our Appendix B, I think. But on a high level, the likelihood of the code reasoning tokens is much higher than the natural language reasoning tokens. Therefore, it gets amplified through GRPO. So to validate our findings, we did an empirical validation. If we just physically turn off this clipping term, so the loss would just be the ratio times the advantage, which is the green line. We see that the accuracy actually do not increase. Another reason why clipping happens is this ratio that I was talking about. So the old model generates a number of rollouts, in our experiments, we use 64. And then we have the batch size. So if the batch size is smaller than the rollout size, let's say like we do one gradient update to get the new model every 8 rollouts, then the new model gets updated actually like 8 times before we calculate the actual GRPO loss. So there's a higher chance that this new model deviates a lot from the old model. So what happens is that we try to not entirely just disable clipping. We make sure that there's only one gradient update from the new model to the old model. So like to ensure that the ratio is 1. So it also does not get clipped. But we didn't want the instability of the completely disabling clipping. And we find that there is also no performance improvement when we disable clipping with this batch size manipulation. And then to the right, we have our initial random reward performance. And then to even like further look into what's happening with the token probability, we see that when we have the clipping term, the token probability of all of the generation tokens keeps increasing, which kind of confirms what we saw like on the loss. And then if we disable clipping, then the high likelihood token and low likelihood token are equally preferred by the loss and the gradient. Therefore, there's no like significant increase in the token probability throughout training. This is slightly correlated with code frequency. So for the random with clipping, code frequency increases with the increase of token probability, but the code frequency kind of stays constant for if we disable clipping. Okay, yeah, so this is kind of like why random reward would work. We took a closer look into the GRPO loss, but then we think there are still a lot of open questions in like the exact effect of clipping, for example. Obviously, it makes the training more stable, but there's the trade-off between exploration and exploitation. We relied pretty heavily on the Doppel paper. So they tweaked the clipping bond to encourage exploration. So we think that this might be what's happening. Like there's more exploration on high probability tokens. Anyhow, if you're interested in details, you can ask more questions or refer to the appendix as well. And then this is fresh off the experiment as well. It's not included in our preprint yet, but we just archived. So you'll see this in a couple of days, but this is very fresh results. What's happening? Like, so we all know that like prompting has a significant effect on the model's performance. So as we showed earlier, if we just prompt the model to, oh, let's solve this problem by Python, we saw like a 20% or like improvement on 1.5B and like a 14% improvement on 7B. So we thought to vary the prompt that we use, both system prompt and user prompt, to see like what is the effect of different prompts on the model's performance and also on RLVR training. So the default prompt is what we have been using for all the previous experiments. So we just like have the like tell the model to put it in a box, which is appended by default for Koehn math models, and then just have the math problem. And then so we tried this other prompt where we just tell the model you're a helpful assistant, and then we say math problem, and then the math problem. So note that like this one, we actually don't tell the model to put the answer in a box. So the model is not explicitly instructed to put it in a box, but we find that like it still does it most of the time. And then we try to replicate to other papers with their prompts, and then to observe what happens with all of these different prompts. So interestingly, all of these prompts show similar trends when we do RLVR training on both ground truth and spurious rewards. But note that they do have like slightly different, or actually very different starting accuracy, which I'll show later. So yeah, like let's say like the default prompt is like 0.49, and then math problem is 0.59. So very interestingly, if you don't even tell the model to put it in a box, the initial accuracy is higher than the default prompt. And also these two prompts that we took from prior work also has pretty good initial accuracy. But what I personally think is the most interesting is we developed this new thing called spurious prompts. So what happens is there's the lip-sum placeholder in LaTeX. We just use that, try to control for the length of the prompt to be similar to this prompt from prior work. But then this text doesn't mean anything, right? And then we tried to use the spurious prompt, and we observe a crazy high step 0 performance. And after RL, there's also like a gain from RLVR on random rewards. Although since the initial performance is a bit higher, the RL gain is less. But then there's still like a 9% gain just from random rewards, which we think is extremely interesting. So you might think that like the prompts might just be teaching the model to follow the format better. Therefore, like, and the RL is also trying to teach the model to follow the format better, therefore the higher performance. But if we go back to think what the prompt actually contains, the math problem prompt and the spurious prompt are not explicitly telling the model to follow the format, but the percent parsable responses is still quite high. That means Koehn math models can follow formats pretty well since the before post-training. And then for example, other prompts that like is like contains more information or more prompt engineered, they do follow the prompt pretty well. But then the step 0 performance, these are all computed with 0 temperature. Actually, it's actually lower than just using our randomly generated spurious prompts. So we think that there's definitely a lot of open questions here on like what is the like I guess spurious effect of prompts on all of these models. We definitely should I guess figure out like a unified way to measure all of these models. But realistic constraints is just that like all of the evaluations is extremely noisy. So as long as any paper can ensure that your evaluation before and after your proposed method is consistent and you do enough populations, it should be pretty reliable results. So yeah, this kind of finishes the content that I'll cover today. So what this means for RL or like post-training in general. So we think that first of all, proposed RLVR methods should definitely be validated across model families, compared against spurious baselines to show the actual gain of the proposed method. For example, we saw that training on ground truth is not that much better than training on format reward or random reward. And then much of the gains from at least academic scale RL might be from just eliciting pre-existing capabilities. So instead of thinking that, oh, like RL is dead, I actually think this opens up a lot of possibilities for future work. For example, we can think about instilling desirable capabilities during the pre-training and mid-training stages to enable more effective post-training. Yeah, I think this is the end of my slides. Here's my awesome collaborators. It's a really fun project co-led by 4 of our colleagues. And then if you haven't seen the blog post, feel free to scan the QR code and read the blog post. And our archive draft should also be coming soon. Yeah, let me know if anyone has any questions. Happy to answer any questions.
Yeah, I mean, I think this is a great piece of work and a great sort of focus. It's kind of like at the intersection of capability research and mech-interp, right? Where I think really what you want to do is you want to like maybe start with like some super small models and like train them to have do some pre-training to try to get to some base level of capability and see exactly how that interacts with eliciting those behaviors through RL. And so I think you kind of need to, yeah, mess with the, like you were saying, mess with the base model beforehand, right?
For sure. Yeah, I think it's actually super exciting because the only 2 capabilities or like pre-existing behaviors that we looked into is code reasoning and then like repetition. So these are like very like easy to verify behaviors. But there's also like other papers saying there's like more complex like cognitive capabilities that are important for like problem solving. We didn't look into it because it's hard to verify. We can't just like prompt GPT to identify that during training. But we think that like all of these behaviors would be helpful for post-training, and post-training is eliciting some of these at some point. So personally, I think it would be the easiest to like start from like a small but reasonably large enough model to try to instill these behaviors and actually like see how difficult it is for RL to elicit different types of behaviors or whatnot for like different tasks.
Yeah, I mean, I don't think it even needs to be sort of that complicated, right? Like, so you can do like really simple ones, like you could pre-train a model to like just be really good at solving anagrams.
Yeah.
Right. Yeah.
And yeah, that's true. That's super interesting as well.
Hi, I had a quick question. Firstly, yeah, thanks for the great presentation. Uh, in the slides where you explained that for tokens which have a high probability, you would have a like wider margin because of the high initial probability of the token. So the magnitude of the gradients would be larger. They wouldn't be clipped.
Mhm.
Uh, I was just wondering, like, since the magnitude of the gradients is like proportional to this clipping, like this term into advantage, so would the high probability tokens have a lower advantage because mostly you would be getting them right?
So yeah, I guess that's a good point to look at, to think about the magnitude of the gradient. We didn't exactly look into like the detail of that yet, but what we're saying is that like there is no gradient if it gets clipped. So
Okay.
there's a larger window when the high probability tokens do not get clipped.
I see.
But yeah, so this is kind of just like an intuitive analysis, but not like in a way like a theoretical proof on like what's happening. Yeah,
I see. Yeah. Yeah. Thanks a lot. Yeah.
that makes sense. Yeah. Is there any other questions? And I guess if you're interested or like come up with more questions after the talk, feel free to email any of the.
So I had a query regarding clipping too. Since I think so with the bias, I think so that could also inadvertently suppress the discovery of new reasoning strategies there. Yeah. So I was like thinking, maybe how does this affect the generalizability of RLVR methods?
Yeah.
Yeah. So like in that sense, will it uh, be easy to generalize?
Yeah, that's a good question. Yeah, I agree that like it probably would inhibit some sort of exploration on new abilities. So here, what we're trying to say is not that we should turn off clipping or like we should have clipping or anything. It's just that like we want to see under expectation of like zero advantage at all, like what is happening, like why is the model even changing at all with the zero advantage. So in terms of the exploration and exploitation trade-off with respect to clipping, if we keep rewarding high probability tokens, it definitely it focuses more on exploitation rather than exploration, which is why there's this Doppel paper that I mentioned. They try to adjust the clipping bonds so that they can have more control on this trade-off to achieve better performance. And what they do is they actually kind of train on ground truth to improve the performance. But what we're doing is kind of just like analysis on like under uniform random reward, what is happening. So yeah, I agree that this exploration problem is super important in like a lot of RL algorithms. And yeah, there's still a lot of future work left on like how do we find the best balance of both.
I mean, the more I'm thinking about this, the more I think it's kind of like the clip higher that they introduced in the Dapo paper, right?
Mm-hmm.
I mean, that seems almost directly addressed at the clipping bias that's going on here, right?
Right. Like, I guess there is a way to intentionally adjust the clipping bound so that it balances, it reflects perfectly well what your advantage is. So there's a way to adjust this bound such that if the expected advantage is 0, we should also have an expected 0 gradient. But yeah, the default GRPO is not currently doing that.
Plus, like in the reward design sense, like you had a section that specifically caters to the sensitivity of the results to the specific design of the spurious rewards versus the weak rewards. So, for example, would slightly different randoms reward probability or incorrect label distribution kind of yield similar gains there?
Sorry, do you mean this part where?
So I was thinking, like, let me try to rephrase it. So, like, how sensitive are the results to the specific design of spurious rewards here?
Yeah. I think that's a good question. So we actually see like quite a lot of like noise, which is why we like, especially with the no clipping, there's like very unstable. So we did a lot of random seeds to show the pattern. But in terms of like the sensitivity of the training with respect to different, I guess, degrees of like spurious rewards, I guess this shows some of that question, where like we can still see that like higher quality rewards such as ground truth and majority voting would still give you the most gains, but then more spurious ones like random and like formats, it still gives you gains, but not as well as ground truth. So let's say if all the RL algorithms are validated compared to the format reward, the actual like meaningful gain of ground truth is actually this ground truth result minus the format result.
Yeah, and like could also the effectiveness of this spurious reports diminish or improve with the scaling? Like how does this scaling effect comes into consideration?
Yeah, we only trained 1.5B and 7B models for academic compute. So yeah, like we draw our conclusions only on small scale models. It is highly possible that like larger scale RL can show like, I guess, more impressive gains in like actually learning reasoning abilities. And my personal take is that maybe spurious rewards would not work as well on like a huge scale RL training. But yeah, that is TBD on future experiments. If anyone has the resource, you should run it and see.
Thanks.
I wanted to bang on about Dapo a little bit more. So like Dapo, it's removing the KL divergence term entirely, right? And so that's going to allow larger distributional shifts. And so how would that work in your setup? Like, so I'm trying to think sort of when is the distribution? I guess you're already kind of answering the question when the distributional divergence is beneficial versus harmful, but like, yeah.
Yeah, so I guess to answer the first part of your question, we also don't use the KL term in all of our training. Yeah. So this is kind of standard in like a lot of recent RL work because this ratio of the new and old model to some extent already ensures the distribution stays relatively stable. in the second question, in terms of the, sorry, can you actually repeat the second question?
Well, I guess what this is, I mean, one of the main sort of upshots of the work is that, there's beneficial patterns or you're suggesting that there's already beneficial patterns that exist in the base model. And so, but when you're removing the KL term, you're, I think, allowing for larger distributional shifts, right? So I'm trying to sort of reconcile those two things.
I see. I guess in terms of removing the KL term, it does allow for like larger room for like distribution shift. But again, if this distribution shifts too much from the current policy to the old policy, then it will get clipped. Then we don't actually get an update when the shift is too much. So the control that we would have gotten from KL is on a high level already ensured by this ratio and the clipping term. So when we remove the clipping term, we do allow for larger range of, I guess, distribution shift or exploration. But because, again, when we remove the clipping, we only ran on like random rewards with the advantage being 0. So the exploration gets sort of canceled out to be 0. We do have an experiment that we didn't post on running the GRPO loss with no clipping, but on ground truth. We find that the token probability increases pretty fast, and it also converges to like a pretty high performance, but less with more variance. So I guess like we do empirically show a lot of these intuitions, but it's not like theoretically or like mathematically proven what exactly will happen with the clipping term and with the KL.
Cool. Thanks a lot.
I think we can conclude the session here. We are 4 minutes above the time. Thank you so much, Stella, for your time and the informative talk.
Yeah, of course. Thank you for having me. Bye.